In this video, we want to take a look at vectors in a different light. We think of them more as algebraic objects, and we do that by sticking them on a coordinate system. So if I'm just in the plane, so I've got my standard coordinate system here, take a vector, any vector, and we're going to put it in what's called standard position. So no matter where it starts from, we're going to pick it up and we're going to, what just happened here? We're going to pick it up and we're going to move it until the initial point is at the origin. So every vector, when it's in standard position, has its initial point at the origin. Then we look at where the terminal point is. Well, the terminal point is going to have coordinates, let's say A, B. So if this is the vector u, I'm going to say that u is equal to, and I make a notation's a little different in different places, AB. I use pointy brackets, and I've seen other books use it. I think our calculus book uses the pointy brackets here. The linear text that we're using just makes it look like, you know, round brackets, just like parentheses. So it's really hard to tell the difference between the point AB and the vector which is in standard position pointing to that point AB. I make the distinction, usually I use the round brackets for the point and the pointy brackets for the vector. Actually, it turns out that there's so little difference between them that it doesn't matter whether you distinguish that one is a point and one is a vector or not. They behave the same way. So, but the idea is, in the plane, take any vector, stick it in standard position, put the initial point at the origin, and look at where the terminal point is. The coordinates of that terminal point will be what we use for the name for that vector. Vector u is a comma b. Okay. In 3 dimensions, you'd have a comma b comma c. You'd have 3 coordinates for the terminal point. Make sure that the vector is in standard position, because that vector, once it has the name a comma b, I don't care if you draw it in standard position or you draw it over here, it's still a comma b, because if you picked it up and put it in standard position, that's where the terminal point would be. Now, just some calculations of things. If you have a vector here that's not in standard position, so if I had a vector from P to Q, I'm wondering if I can just use the coordinates of P and Q to help me figure out what the vector is, actually we call these as rather than coordinates of the point, we think of them as components of the vector. We have the x component and the y component. Just terminology that we use. So here we go. Think about the vector. I'm trying to come up with a vector PQ. But think about the vector OP, where O is the origin here. So OP is the vector that starts at the origin and heads out to P. I'm going to give that the name x1, y1, where x1 is the x coordinate of P and y1 is the y coordinate of P. And then likewise, I've got this vector OQ, which starts at the origin and goes out to Q. Well, that has the name x2, y2, because the coordinates of Q are going to be x2, and the y coordinate is y2. Okay. So now I want to come up with the vector PQ. Well, notice this is the vector that goes from here to here. If you thought about the parallelogram generated by OP and OQ, or sometimes we just say generated by P and Q. If we think of that parallelogram, this is the diagonal, not the long diagonal where you would add the two of them up, but it's the one that joins endpoint to endpoint here. Now it's subtracting, and then it's like, oh, do I do P minus Q or Q minus P? And look, I'm starting here. I'm going backwards on P and forwards on Q. So that was a plus Q and a minus P. So this is Q minus P. And the way we get those coordinates now, we haven't defined how to add and subtract yet, have we? Let's come back to that. Maybe you can see what we have to do. Actually, it's probably not too hard to see what we have to do. The x coordinate is this distance, the y coordinate is that distance. So this would be the difference in the x values, x2 minus x1, and the y component here would be the difference in the y values, y2 minus y1. So to get the vector between 2 points, you just subtract the coordinates, end point minus start point, right? I'm ending at Q, starting at P, and that's the vector that I have. Notice that even in standard position, if you think about the vector from 0, 0 out to AB, you're doing A minus 0 and B minus 0 to get those components. Okay. Now, the book gives a definition at this point, which I find kind of interesting because they give the definition and then they kind of forget about it. They define this: if n is a positive integer, then an ordered n-tuple is a sequence of n real numbers, v1 up to vn, put in parentheses with commas in between here. Let's put one more comma right there. The set of all n-tuples is called n-space, and we denote it by a boldface r raised to the n power. This, when we talk about working in the plane, it's R2, and working in space, it's R3. But if you have more coordinates than that, then it's Rn. Now I say this is, the book is kind of weird on this because you can think of these n-tuples either as coordinates of points, or you can think of them as components of vectors in standard position. The book just completely makes the transition. They define n-tuples, and then immediately they just start calling them vectors. It's like, wait a minute. Vectors are arrows. These are lists of numbers. Well, we're making essentially a one-to-one correspondence between geometric vectors, arrows, and n-tuples. If I'm in R2, if I'm in the plane, then for each point in the plane, there's a vector that starts at the origin and points to it. For each vector, once you put it in standard position, it points to a point. There's a one-to-one correspondence between vectors in R2 and points in the plane. Likewise, there's a one-to-one correspondence between vectors in R3 and points in space. So are these n-tuples just lists of numbers, or are they vectors? It's like, well, let's define how we add these things and multiply by scalars and see that they behave in exactly the same way that our geometric vectors did. So some things that we need to do in order to do that, I need a zero vector, I need to define some operations. Notice that there's a very special vector that looks like this. I denote it with 0 with a little vector symbol over it. And it's 0, 0, all the way up to 0. That is, all the components are 0. In standard position, whether I'm in the plane or space or more dimensions, this thing starts at the origin, because all of them start at the origin. What just happened? They start at the origin here. But where do I go? I end at the origin. So yeah, that's a really short vector. Has length 0. And it's what we call the zero vector. Now let's look at how we do some arithmetic with these things. First of all, I need to make the definition of when our two n-tuples, or vectors in Rn, however you want to think of them. When do I know when they're equal? Well, it's just like with matrices. I'm going to say that these two vectors are equal if the corresponding entries are equal. All the corresponding entries are equal. So v1 is equal to w1, v2 is equal to w2, and so on, all the way down to vn equals wn. That's when I know that the two n-tuples are equal, or the two vectors are equal. Okay. Now, a little arithmetic. How do I add? So given two vectors in Rn, so v1 and w, which I'm thinking of as the same coordinates as what I had there, same components, I add them by adding corresponding entries, kind of like we did with matrices. If you just think of this as one row matrix and another row matrix, and you add them together, then you add the first entries, you add the second entries, and so on down the line to the nth entries. Okay. Scalar multiplication. If I've got a vector in Rn and a real number k, then k times this vector, or this n-tuple, is just k times the first component, k times the second, and so on. Okay. This agrees with our geometric definition. For instance, here's two vectors. If I add them geometrically, I'm going to take vector v here, no, not that button, this button. I'm going to take vector v here and add it on, oh, I wanted to Don't move it yet. I wanted to copy this thing and paste it. There we go. So I added on to U. Component-wise, U plus V is this vector here, and I need to know, because it's in standard position, what are the coordinates of this point? Well, the thing is, if I know the coordinates of U, so I know the X and the Y coordinates of U, so what is this? Let's say X1, Y1. And I want to add on to it the coordinates of V. Well, just look at this. Think about this triangle right here. Up V. As I pick that up and move it, that just moves right over to there. So the X coordinate of this point is the X coordinate right here plus that length. Well, that's the X coordinate for V. Likewise, the Y coordinate right here is first you've got to get all the way up to there, but that's the Y1, and then you've got to move up a little bit further. Well, that's the same amount as this. So the total X coordinate is the sum of the two X coordinates, and the total Y coordinate is the sum of the two Y coordinates. And hence the way we define addition agrees with our notion of adding those two vectors. Likewise with scalar multiplication, that if you've got the X and the Y coordinate here, and you're then going to scale this thing. Come on now. Try this again. No, try it again. Come on. There we go. Paste. So there's the vector 2 times U, but if you look at the X component is this X component plus that X component, and the Y component would be this plus that. And so you just multiplied both components by 2. That is, multiplying the vector by 2, multiplied the X component by 2, multiplied the Y component by 2. So you can think of these vectors either as arrows or as n-tuples. Whatever serves your purpose, the two notions work together. Here we go, additive inverses. Notice that for each vector I can construct a vector where I just make the signs of all the components the opposite of whatever they were. This would be the additive inverse. Notice if I did V plus negative V, I'd be adding V1 plus negative V1, comma, all the way up to Vn plus negative Vn, which is maybe easy to see is just the zero vector. And that's the definition of an additive inverse. If you add it to the thing you started with, then you end up with the zero vector. Subtraction then is defined in terms of just component-wise or adding the inverse, either way you want to think of it. V minus W is you're subtracting the components, or maybe it's adding the additive inverse of W, right? Maybe you think of it as V plus negative W, V2 plus negative W2. That's a W. So there's arithmetic with vectors in Rn.